Okay, so welcome back. So this is the last afternoon of the first week of the ELGA, and it's my pleasure to announce the fourth lecture of Joaquín Moraga, and today he will tell us about cluster type Fano varieties. Please, Joaquín.
Good. Can you hear me? Yes, that's better. And I didn't say anything that important. So let's start with the following definition that I will use heavily in a second. So we say that two log pairs, we say that two log pairs xb and x prime b prime, so this could be pairs on different varieties, are quotes crepant by rational equivalent or crepant by rationally equivalent if there exists a common resolution P from y to x and Q from y to x prime such that the pullback with respect to P of kx plus b is actually equal. So this means equality as pullbacks of Q divisors. Okay, so just to emphasize that here, I want these two divisors. Well, I haven't written the second one yet, but it's what many of you may expect. So I want these two Q divisors to be equal to each other, not Q equivalent or numerical equivalent or anything weaker. So, which actually it will be very important. So this is called crepant by rational equivalence because one can show that if two pairs are, well, first you can see that we are asking for a common resolution, right? So this word makes a lot of sense. The underlying varieties must be birational themselves. And then the word crepant is here because one can show that if this condition holds, then they have the same discrepancies. So there's no discrepancies, so hence we use the word crepant, which is, I think, a word invented by rational geometers, as far as I know. So examples. Are there any questions? The word is very likely, right? He's the one that introduced all these funny words. So some of them I like, some of them I don't like a lot, but let's not get controversial. Flip is amazing, crepant is amazing, but Tom and Jerry's I don't like. Okay, so examples. So let's say that you start with P2, and then you take a nodal cubic. Okay, so something that you can do is the Cremona transformation. So for instance, if you perform the Cremona transformation based on these 3 points, right? So this is a fun exercise. So what do I mean with Cremona transformation based on these 3 points? You can move these 3 points to the torus invariant ones, right, with an automorphism, and then just apply x going to 1 over x, y going to 1 over y, z going to 1 over z, like meaning the usual Cremona, the standard Cremona transformation. So if you do this, then when you blow up these nodes, you will extract a new curve with coefficient 1, which actually will get mapped, will end up being, let me think for a second. I think that will get mapped to a conic here, and then this curve, this cubic, and I think the cube gets mapped to the conic, and then the exceptional gets mapped to the line. But it doesn't matter. What happens if you pull back this pair and push forward here, you will get a line with a conic. Okay, I don't remember if the line was exceptional or the conic was exceptional, but that's not a big deal for the picture. And then if you perform another Cremona transformation based on these 3 points, so a nodal point and any other 2 points, then what happens is that you get P2. If you pull back this pair and then you push forward here, you get P2 with the 3 lines. So these 3 pairs are Crepin birational to each other. So on the other hand, you can observe that if you take P2 and a smooth cubic, meaning P2 and some elliptic curve inside it. So I'm very bad at drawing elliptic curves, so okay. There's people that draw them like if they knew what they were doing. Okay? So you can check that it doesn't matter which transformation you take. If you take a self-transformation from P2 to P2, and then you pull back, push forward, then everything that you will get here, well, you could get something, some pair or some soft pair with negative coefficients. But if you want to get an actual pair here when you pull back, push forward, everything that could happen is that you end up choosing a different elliptic curve. So essentially, what I want to emphasize is that the existence of these nodes is a birational, it's a Crepin birational invariant. Okay? So let me make this statement more precise. Well, the existence or non-existence of these nodes is a birational, is a Crepin birational invariant. So meaning that it's invariant under Crepin birational equivalence. Before I keep moving, let me mention that in this case, let me, okay, so continue the definition over here. In this case, the map, the birational map, phi going from xb to x prime b prime is called a Crepin birational map. And of course, this Crepin condition depends on b and b prime, right, because they appear in this pullback. It's called a quotes Crepin birational map. Okay? So this is how Crepin birational equivalence work. And let me write a general statement. So you can take this as an exercise. It's actually not hard to prove. Why these 2 points?
Yeah, because like one point is apparently intersecting with each other, but why other 2 points are also full nodes?
Translation?
The middle one looks like the first picture of the mid red point looks like those.
This is a node, yes.
Why other 2 are also nodes?
These 2?
No.
No, these 2 are not nodes. These are smooth points. So the construction was perform the Cremona transformation based on 1 node and any other 2 smooth points on your nodal cubic. Yeah, the others are not nodes. Okay, so let's see the following proposition, which give us some basic properties about Crepin birational equivalence. So proposition. Let xb be, and I forgot one more thing, sorry. The notation for Crepin birational equivalent is C beer, okay? Crepin birational. So if you just write beer, this means that the models are birational to each other. It just means that the underlying varieties are birational. But if you write C beer, you mean these stronger conditions that the pullback of the log pairs of the canonical plus boundary are equal in some higher model. So let me write it here. This means Crepin birational equivalent. And these are 2 log pairs, okay? So normal quasi-projective. Then the following conditions are satisfied. XB, 1. XB is log Calabi-Yau. I will abbreviate by CY. If and only if X prime B prime is log Calabi-Yau. 2, if MKX plus B is 0, then MKX prime plus B prime is 0. So if you know the index of a divisor is the smallest multiple that will make it Cartier the points. The index of a Calabi-Yau pair is the smallest multiple that make it linearly trivial. So essentially, this line says that if they are log Calabi-Yau, then they have the same index. 3, the co-regularity of XB is equal to the co-regularity of X prime B prime. And 4, XB is epsilon log terminal for some choice of epsilon, if and only if X prime B prime is epsilon log terminal. Let me abbreviate by epsilon log. So essentially, this says that the discrepant birational equivalence preserves somehow the curvature, the index of the canonical. So like somehow this gives you control on the singularities. The last one also gives you a control in the singularities, and this gives a control in, well, the singularities as well. So essentially, crepant birational equivalence preserves curvature and singularities. That's more or less the idea. Okay? So this is the statement. These two are statements about the curvature. These two are statements about the singularity. Okay? So now let's go with the main definition of these mini-curves, which is the definition of cluster type pairs. So in what follows, I will use this notation, which is non-standard but is quite useful. So I will write, so in what follows, sigma n is the sum of the coordinate hyperplanes in Pn. So you can ask, well, which ones? Well, it doesn't matter, right? They up to isomorphism, there is just one choice. And why this notation? Because you will often write something like this, right? Or you can write something like this. Well, this is 0. Well, but let's just remember the important information is sum and n, right? So this is where the notation comes from. So now let me give the main definition. So let me start with this with this one. So we say that a log Calabi-Yau pair definition. So a log Calabi-Yau pair is, quotes, log rational if, I forgot to give it a name. A log Calabi-Yau pair XB is log rational if XB is crepant birational equivalent. So we say that this was severe, 2Pn sigma n. Of course, for some n that must be the dimension of x, there is no other choice. So this is what we called crepant birational equivalence, right? Essentially, it means that there exists a crepant birational map from Pn sigma n to xb. So let me write it. Let's write the Calabi-Yau pair on top because then I have more room. And now I will write on the other side something that is very non-standard, but you will see that it will make a lot of sense. So actually, I may try to prove it, or at least give you a sketch that this definition fits with the usual definition that you see. So a local Abiyao pair is, quote, toric if there exists a crepant birational map phi from Pn sigma n to xb and phi, so the restriction, so let's say the map from the tori to x minus b is small. So what this means, it means that if you look at this map, the exceptional loci is small in both varieties. Okay, so if you look at this definition, you're like, okay, this is not the definition of a toric variety, right? But it turns out to be equivalent. So what is the point? The point is that you have this pair. So a sketch that this is actually a characterization of toricness. Sketch that this characterizes toricness. So why is this definition somewhat nice to me? Is because it's like it's a definition that sort of forgets the Druce action, right? I mean, you don't have to check any action. You just need to think about birational maps. And sometimes that's slightly easier. Okay, so imagine that we have this crepant birational map. So what it means that this map is small from the tori to x minus b. It means that all the divisors that you're extracting from x to Pn appears in B. So this means that all the divisors that you're extracting actually appear with coefficient 1 when you pull back kPn plus sigma n. So the exceptional, okay, I will do the proof. Actually, let me not do something stupid, and let me write the proof from the top to the bottom like a normal mathematician. Going up. Okay, so let's say that we have phi from Pn to sigma n to xb. So what it would mean that that the map from the tori to x minus b is small, then the exceptionals of phi inverse are inside B, right? I mean, are inside components of B, to be more, components of B, right? So, but these two pairs are crepant. So it means that all the exceptional divisors of the inverse appear with coefficient 1 when I pull back kPn plus sigma n. And one can check that those divisors are precisely torus exceptional divisors for this pair. All the divisors that you will extract with coefficient 1 in a Higgs model of this pair are precisely the toric valuations, are the ones that you get by blowing up the strata many, many times until you extract them. So in particular, we can extract all divisorial valuations corresponding to components of B, divisorial valuations corresponding to components of B, by blowing up a strata of sigma n. Okay, so to be more precise, you have to blow up a strata of sigma n or a strata that appears in higher blowups. I'm being a little bit imprecise. But the important point is that if you repeat this procedure, you will just get a toric variety. So you will have a diagram like this. So you have Pn sigma n, Pn sigma n. Then you will have a toric model B T sigma T, which is just a toric blob of Pn. And now you will have a projective birational contraction. So meaning that this map that goes diagonally does not extract divisors. It only contracts divisors. So this is a, let's call it, so I use phi, let's call this psi. So psi is a projective birational contraction. So then you can do the same process here, and yeah, so now I have to go slightly quicker, so so you can do the same process here and find, so essentially you can find a small map, so let's call this, let's just write that this is a small. You can find a small map such that x prime actually has a morphism to x. Okay, because essentially the exceptional loci of this is small, so one can do some toric transformations such that this is actually a morphism now. So in other words, you can pull back an ample here and run the MMP for the corresponding divisor until it becomes semi-ample. Okay, so if you have a small model of a toric variety, then it's toric. X prime is toric. And then if you have a toric, a projective, well, if you have a contraction from a toric variety, the image is also toric. Because the contraction is given by an ample divisor on X prime, by a semi-ample divisor on X prime, and you can always take it equivalent to a torus invariant semi-ample divisor. So then the morphism will endow X with a toric structure. Okay, so at this point, you may be at least slightly, I mean, I hope that you got the idea of the proof, but you should be at least slightly confused why we take this so non-standard definition. So the whole point is that this non-standard definition will motivate what I will write next, right? So we're asking that this morphism is small. So now I can try to weaken the condition of being toric, right? If you just think about toric varieties as being n-dimensional varieties with n-dimensional transactions, with some caveats, maybe say normal and so on, then what is the natural weakening of that definition? You naturally arise to complexity 1 varieties, which are n-dimensional normal projective varieties with n-1 dimensional torus actions, right? So that's one weakening of toric varieties, and there's a whole of literature on the developments of complexity 1 varieties. Alvaro here, if he's here, is an expert on the topic. Antonio is also one of the experts on the topic. But then now we have another definition for toric varieties. So let's try to weaken this one and see what theory does it leads to. So this is the motivation. And how do you weaken this theory? How do you weaken this condition? If you just replace the word small by nothing, right? If you delete the whole condition, you get to log rationality. And then you can ask, well, how do you weaken in the middle, right? You can ask that it's only small in one direction, right? That it doesn't contract divisors or it doesn't extract divisors. So if you ask that it doesn't extract divisors, then you can actually prove that you again get to toric varieties. So what is the weakening between log rationality and toric? Is that this guy doesn't contract divisors. So, and this is the middle definition. A log Calabi-Yau pair, XB is cluster type if there exists a Crepin birational map phi from Pn sigma n to XB such that, so now let me write something slightly different, which is equivalent to what I just said. The codimension in Pn, of the exceptional loci of phi intersected with the algebraic torus, well, the standard one, Pn minus sigma n, is larger or equal than 2. So it just means that this map doesn't contract any divisors. I'm just writing some slightly different definition. So now we have these new classes of Calabi-Yau pairs. Log rational, well, toric is not new, but we have these new two classes, log rational and cluster type. And we will study their properties, and we will see if this leads to classes of Fano varieties which are interesting and have moduli, right? So remember from the first lecture, I say that we all love toric varieties, right? Because they can explain so concretely. You can put them in the computer. You can do computations, right? That's amazing. But what is one of the weakness of a toric variety when you are trying to study Fano? Toric varieties that they tend not to have moduli, right? If you look at the moduli of all Fanos, they tend to just give you isolated points, so they're not very good to test conjectures, right? It will give you only discrete data. So my proposal is that if we give a definition of cluster type Fanos, this should be pretty similar to the toric ones, but they admit moduli, and there is a hope that we can give a combinatorial description of these ones. So that's what I will explain in the rest of this talk. Okay, good. Any questions or comments before we start? Oh, yes, that's yes. So let's see. Well, for log rational, okay, let me. This has a little bit of water. I hope it's okay. So let me think for a second. I don't know if I can write here. Oh yeah, that's fine. So for instance, this pair that we were describing before, P2 with a nodal cubic, this is log rational, right? Because and this is clearly non-toric, right? I mean, if you have, the automorphism group in this pair is rather small. So this is a log rational example. And actually, this one is cluster type 2. We will prove that later. But however, there are some. Let me write this now. So there are Fano surfaces. I will explain this in detail in a few minutes. There are Fano surfaces X admitting log rational structures, log rational Calabi-Yau pairs XB, but no cluster type Calabi-Yau pair. I will try to come back to this in a second. But no cluster type Calabi-Yau structure. So currently, it's a bit unclear if log rationality, cluster type, well, it is very clear that toric is much smaller than cluster type. Cluster type allows you to do a lot of blow-up. So essentially, cluster type allows you to do toric blow-ups, but also blow-ups at these points. So it gives you quite a lot of rigidity. And then log rationality allows you to do blow-ups at these points, but also contracts a lot of curves inside the torus. So it is much larger. Each class is quite larger than the previous one. Okay, so let me explain now what are log rational Fano varieties and cluster type Fano varieties. But the definitions are like sort of self-explaining, right? So we have a definition for log Calabi-Yau pairs. We want to extend it to Fano varieties. What you ask is that it admits a log Calabi-Yau structure with blink condition, where blink was the condition for log Calabi-Yau pairs. So let me write here definition. So a Fano variety X, and remember that for me, when I say Fano, I just mean log terminal Fano, not necessarily smooth, is, quote, log rational type. Remember that we use this word type every time that you need to throw some boundary for the object to satisfy the condition. If there exists b larger or equal to 0 on X, such that XB is log rational. And secondly, a Fano variety X is said to be cluster type, and now we have the definition of the title. X is quote cluster type if there exists b larger than equal than 0 on X such that XB is cluster type. Okay, so note that these definitions actually make sense for any algebraic variety, right? It doesn't need to be Fano. I mean, I'm not using any Fano-ness in the statement, right? But we know that, for instance, corregularity zero Fano varieties, they often have elements in negative kx. Right? If negative kx is empty, then it's impossible that this holds because log rational pairs and cluster type pairs, they both have index 1, which means that you have to find an element b actually in negative kx, in the linear system negative kx, right? So you cannot find a boundary v with fractional coefficients, right? This is the first proposition I wrote today, that the index of the pair is preserved under crepant rational equivalence. So let me just make the remark that if x is log rational type, implies that negative kx is non-empty and that the absolute corregularity is 0. I mean, you can define these notions for non-Fano varieties, but in Fano geometry, you tend to find a lot of examples among corregularity 0 pairs. So I've been mostly focusing on this part of the picture. So let's draw a table. Well, this is not a table, a diagram. Now, just summarizing all the concepts that we have introduced, and I think I didn't have to use this one. Okay, good. So I think I'm making a mess with the with the blackboard. Okay, it will be fine eventually. I think this tends to stabilize. So here we have all Fano varieties. And as we said yesterday, inside Fano varieties, you have these two interesting classes, which are rational Fano varieties. And I'm not going to talk about how to detect rationality. Okay, this is a very old problem. There is a lot of literature, and in the recent years, meaning last 20 years, people have understood that this problem is extremely delicate because it has abstractions from number theory, from combinatorics, from topology. Like there is a lot of abstractions for rationality. Inside here you have corregularity equal to 0 Fano varieties. And here I should say absolute corregularity. So sorry if I'm sometimes a bit I don't mention this word. So, and inside this, so what we mentioned, I mean, of course, if you're log rational, x must be rational, right? And here we observe that if you're log rational, then you have absolute corregularity 0. So the log rational Fanos, or log rational type Fanos, are inside here. And then inside the log rational Fanos, you have cluster type Fanos. And then inside cluster type Fanos, you have toric Fanos. Okay, so what we agreed on Monday is that this is too hard. Right? Maybe you don't agree with me, but okay, that's fine. And we also agree that this is not too hard. It's also not too easy. But the main problem is that they do not have moduli, right? And that's a problem to test things. So now I will try to convince you. I don't know if I will achieve that, but I will try to convince you that many Fano varieties that appear naturally are cluster type. Okay? So let's try to prove this. So let's prove this. And this theorem I want to prove fully. Well, almost. Okay. So the following theorem I will try to prove in as many details as I can, because I think it's like a foundational theorem for this theory, although it's quite easy. So it's beautiful. So the theorem is the following. Theorem a general, no, first a smooth Fano surface, a smooth Fano surface of volume at least 2 is cluster type. So now we have a lot of moduli, and actually we're hitting all smooth Fano surfaces of volume at least 2. And a general Fano surface of volume 1 is cluster type. And this is not true for special Fano surfaces of volume 1. So if you prefer the opposite language, here I'm looking at del Pezos of degree at least 2, del Pezos of degree 1. Okay, proof. I want to endow these varieties with a Calabi-Yau structure. And I know that these varieties are blow-ups of P2 in at most 8 points in general position. Oh, well, there is one case that is not a blow-up, it's P1 times P1, but that's fine because it's historic. Ah, yes, thank you. Thanks. Yes, I say general, I didn't write it. Because there is these special elements in the family that have no nice anti-canonical elements. So all the no nodal anti-canonical elements. So then we're blowing up these points. Let me write P1 through P8. So if you have volume at least 2, then you're blowing up at most 7 points, and then you can always find a nodal curve, a nodal cubic through all these points. And if you have if you're a smooth Fano surface of volume 1, and some polynomials in the Weierstrass equations do not vanish simultaneously, then you can also find a nodal cubic through these 8 points. So what I'm saying is that in all the cases of the theorem, you can find a nodal cubic passing through all these points. So here, we will consider this pair P2, B. And then there are 8 points somewhere that you are blowing up to obtain X. But note that if you pull back KP2 plus B, well, all the points are contained in the curve, so they will appear with coefficient 0 when you pull back KP2 plus B. So this will naturally give you a pair XBX that is crepant birational to this one. So by construction, XBX is crepant birational to P2, V. So now let me argue that P2, V is actually cluster type, right? So what we proved before is that this pair is log rational, right? We did these 2 Cremona transformations, and we got that it's a log rational pair. So now let me argue for you that it's actually cluster type. So here I will be a little bit fast. So you have P2 with the nodal cubic, you blow up this point. Now you are in F1, right? And now the picture looks like this. Let me think, that will be the exceptional that appears with coefficient 1. And here the strict transform of the nodal cubic. Then you will blow up this point, and you will blow down the strict transform of the fiber. And you will do the same surgery on the left. And this is what we call some monoidal transformation. And then you get to, so this is -1. And then we get to F3. And now we have F3 with the toric boundary. So now I can just take a birational map from, like I do a toric transformation to get to P2, sigma 2 with the toric boundary in such a way that this is just an isomorphism on the complement of the boundary. So this is a different way to prove log rationality that actually proves more. Because now let's keep track of the exceptional divisor. So the tori goes to the tori here, right? You can check that this composition from here to here is actually an embedding of the tori in P2 minus the nodal cubic. And then, of course, if you love the nodal cubic, then this map from P2 sigma 2 to XB induces an embedding of the 2-dimensional tori in X minus Bx. So we get that it's cluster type. So every general Fano surface, a smooth Fano surface is cluster type. Okay. Any questions? Yeah, I will get there. But that's a bit too much to hope, because there are smooth Fanos that are not rational. So you have to start digging a little bit deeper into the problem rather than, yep. So, precisely. Oh, because in the definition of cluster type, we have this discrepant birational map, right? And this forces this one to be a log canonical pair of index 1 with corregularity 0. And that means essentially nodal for surfaces. So then you get the contradiction. So we have a very good understanding in the case of a smooth Fano surfaces of which ones are cluster type, which ones are not. So what is next? So once you introduce a concept, okay, so hopefully I introduce the concept and I showed to you that is, do you have questions? I mean, you're asking Fernando, so you can just ask me, right? I'm getting there. I'm getting there because that's actually that's a bit the motivation of this. So let me. Yeah. So now maybe I should explain the name, right? I mean, log rational makes a lot of sense, right? You're sort of making realizing the rationality problem with some logarithmic structure along the hyperplane. But cluster type, I mean. Okay, your question is where did you steal this from, right? And so let's see. So a theorem, so this is to motivate the name. So this was proved earlier this year by Josh Enright that is giving a talk next Thursday, I think. Figueroa and myself, so this year. So Fernando, as we mentioned, is starting his postdoc in Northwestern, and Joshua Enright is currently a grad student at UCLA. So let X, be a Q factorial. So we need some conditions for this. A Q factorial Fano variety, so log terminal Fano variety. Let XB be a cluster type Calabi-Yau pair, or be a, you can just say cluster type pair, right? Because from the definition and the proposition that we prove, it is Calabi-Yau, be a cluster type pair. Then the complement, then X minus B is divisorially covered. I will explain this word in a second. Divisorially covered by copies of GMN. So divisorially covered means that it covers everything except codimension, sets of codimension at least 2. Okay? And what else do we want to say? Okay, and a remark is that in all the examples that we know, I don't know if this, well, yes, in all the examples that we know. O of X minus B. So note that B is ample because we're in a Fano variety and Kx plus B is 0. Right, so negative Kx is ample, so this forces B ample. So X minus B is an affine variety, so this is just a ring of sections of the affine variety. It's a cluster algebra. So, and now people have to ask me, what is a cluster algebra? Well, let me not get into the definition, but roughly speaking, it's pretty much this. It's an algebra whose spectrum is covered by tori, and the gluing functions between the tori respect the volume function, meaning that when you have the transition function from GMN to GMN. This is birational, it's not a morphism. Then the pullback of dx1 wedge dxn over x1 through xn, it's equal to the same thing. Okay. So here there is a little caveat in this remark, is that there is not just one definition in the literature about cluster algebras. If you look at different papers, they tweak the definition a bit, depending on what definition they use for mutations. But I guess I'm getting out of the variational geometry world, and the point is that this remark is with the broadest definition that you can find in the literature, in which they look at this Laurent phenomena rather than just like a linear mutations. Okay. But I have to say that this is okay. Well, I will say more about this in the future. But this is what explains the name cluster type, right? So we don't know if this OX minus B is always a cluster algebra, but it looks pretty much like a cluster algebra. That's the motivation. Okay, so now the next question is, let's say that you pick a Fano variety, and then you want to test if it belongs to these classes that are below it, right? Jenny, you seem unconvinced. No, is it good? Yeah. Okay, so now for a few minutes I will talk about detection criteria. So what do I mean with detection criteria? I will tell you some criteria that you can apply for a Fano variety or for a local Abelian pair to check if it belongs to. Okay, so we already say that this direction, checking if it's here, is very hard. So I'm not going to talk about the rationality problem, but I will talk about detection criteria for all these other classes. So is my Fano variety corregularity 0? We already discussed it yesterday. Here you can use the anti-bicanonical test. Okay, so this sounds fancy, but it's just because of FFMP by FFMP22, you just need to look at negative kx and negative 2kx. Right? So a priori, if you check the definition of absolute corregularity 0, you have to look at all the anti-canonical systems. Right? But we proved that if you have a boundary of corregularity 0, then you have either a 1 complement or a 2 complement of corregularity 0. So you just need to study this two linear system. So in other words, this is, quotes, a finite type process to check whether your Fano variety has absolute corregularity 0. And actually, this finite type process that seems, I mean, you know, some cases it's nice to apply. In some cases it gets very hard, right? Because negative kx of a Fano variety could be, right, pretty large, and negative 2kx could be larger. But at least you're checking something in a finite dimensional space, right? It's something different than other theories where you need to check some condition in something that doesn't look finite type. So what I want to mention is that the anti-bicanonical test has been applied effectively by other authors. So there is a paper that came out in 2023. So they were actually motivated by some questions in mirror symmetry, and it's by Avilov, Prijakovsky. I will do my best, okay? Okay, I think I got almost all the letters. And Loginov in 23. So using our theorem, and of course a lot of explicit birational geometry, they proved that among the 105 families of smooth Fano trifolds, of smooth Fano trifolds, at least 100 families have general point with corregularity 0. with absolute co-regularity zero, general element of the family rather than point. General element of absolute co-regularity equal to 0. There are two families with general element with absolute no, three families. There are three families. And I think these are the, if I remember well, these are the Fanos in the main index with the smallest volume. So pretty similar to what happens for surfaces, that the smallest volumes tend to create some little issues. So there are three that have general element. Of absolute co-regularity equal to 1. And actually, I think that there are two cases that we still don't know the co-regularity of the general elements. I think those ones have the anti-canonical system negative kx. It's not that big, but the geometry of the anti-canonical divisors sort of varies a lot, so it's hard to find log resolutions for all of them. Or at least we don't know how to do it yet effectively. So what this means, so for a smooth Fano surfaces, right, there are 10 families, and the general element of each family has co-regularity 0, right? Actually, the general element of each family in dimension 2 for smooth Fano surfaces belongs to this class, which is like the nicest one. So what they prove for trefoils is that at least 100 out of 105 belongs here. So that's good news, right? Because we're saying that the theory that we're introducing have a lot of stuff inside. And what they do is mostly explicit by rational geometry, but they only need to mix it with some. They need to use this abstract theorem to rule out some cases. I think the three cases that they rule out is mostly based on that. Give me a second, I want to check my timer. Okay, good. So what about testing log rationality, right? So for co-regularity 0, we have this anti-bicanonical test. So now the next question is how to test log rationality. Oh no, I don't. Sorry, I don't know it from the top of my head, but I think this. I think one of them was very simple, maybe like a smooth cubic or something like this. Yes. I think one of them was something quite simple, but the other was maybe some Umemura threefold. It was a more complicated one. So now let's get to how to detect log rationality. So let's say that we have a good detection criteria for co-regularity 0. Now we want a good detection criteria for log rationality. So here the news are not good. So the fact is that we don't know. But we have a conjecture, at least, and that gives us a little bit of hope. So the following conjecture is due to, again, Enright, Figueroa, and myself in the same paper that is called Birational Complexity. Log Calabi-Yau pairs of birational complexity 0. So I can try to get to these words later. But how to detect rationality? This is the question that we will focus on now. So we have a conjecture. But to state the conjecture, I need to write some definitions. So definition. Let XS be a simple normal crossing pair. So meaning that X is smooth and S is a reduced divisor with simple normal crossing intersection. So they intersect like the hyperplanes in AN locally. BS and C pair. The dual complex of the pair, quotes, this is the object that I'm defining, the dual complex of XS denoted by DXS by DXS is the CW complex whose points are in correspondence with irreducible components of S. And K simplices are in correspondence with irreducible components of the intersection of K prime components of S, with irreducible components of the intersection of K plus 1 components of S. And when I say components, I always mean irreducible components, okay? So this is a combinatorial object that just tells you how S intersects, right? You go from a simple normal crossing divisors on an algebraic variety, and then it just gives you some complex. So now how we use this to study Calabi-Yau pairs, or how we use it to study Fano varieties? So let me erase this diagram. So the idea is pretty simple. So you start with a log Calabi-Yau pair, you take a log resolution, and then you look at the dual complex of all the divisors in the picture in the log resolution that appear with coefficient 1. And why we do it this way instead of just looking at X itself, right? Why don't we just look at the Calabi-Yau pair? Because essentially these definitions that are made in some log resolution behave better with respect to rational geometry, right? So sometimes you can have some combinatorial intersection on some variety, but then you do a rational modification and the combinatorics change. So you want to choose some sort of model where these combinatorics stabilize. So definition so let X be a log Calabi-Yau pair. The dual complex of XB actually, if you have an eraser at hand, in this definition, change the X with Y, right? So you don't get confused when you look at the next one. The dual complex of XB is dy delta y equals 1, where ypx is a log resolution of xb, and ky plus delta y is equal to the pullback of kx plus b. Why did I change from? I do this my whole life, that I change from delta to v. My co-authors always complain about this. I tell them to fix it at the end. Okay, so proposition, or actually theorem, due to de Fernay, Collard, and Xu, right? Because if I give you this definition, a priori depends on the log resolution that you pick. Actually, you can keep blowing up more. You can blow up this strata, the strata of the divisors with coefficient 1. And of course, you will introduce more points because you introduce more divisors. But what de Fernay, Collard, and Xu prove de Fernay, Collard, Xu. So two statements, I think this is in 15, is that the dual complex of a log Calabi-Yau pair is well defined up to simple mode of equivalence of pseudo-manifolds. Okay, this sounds very fancy, right? So let me just say it in plain words. if you pick different log resolutions, you can go from the dual complex of one to the other by adding vertices and doing simplicial subdivisions and doing collapses, which is the inverse of simplicial subdivisions. Right. So if we remember the example of P2 and the nodal cubic, P2 and the quadrant line, okay, so this is birational, sorry, and P2 with the 3 lines, what are the dual complex of these 3 pictures? This is just 1 point. Well, this is not log smooth, right? This is the example that fails because there is just one node. So I guess we should draw it like this if we could. But the right way to define it in the log the resolution. So this is 2 points with the lines, and this is the 3 points, well, with a circle around them. So you see that if I keep blowing up more, I just add more dots to the picture, but the topological object is the same. As a pseudo-manifold, then you are just doing collapses and barycenter subdivisions. And the second proposition, which is actually just a consequence of this theorem, is that the dual complex, so if you have 2 crepant equivalent pairs, so XB is crepant birational, sorry, not crepant birational equivalent is what I wanted to say. So you have 2 log Calabi-Yau pairs or just log pairs. Actually, this definition is not just for, this theorem is not for log Calabi-Yau, not only for log Calabi-Yau, but I mostly use it in this context. If you have 2 crepant birational pairs, then the dual complex of one is PL isomorphic to the dual complex of the other. So then we conclude something from this theorem and this proposition is that the dual complex of a cluster type pair or a log rational pair must be a sphere because the sphere is the dual complex of the hyperplanes in the projective space. So we get a test. So we do not know yet, or we don't have the complete answer of how to detect log rationality, but we have at least one test. We need to seek for spherical dual complexes. Right, so some sort of structure that looks toric. And some other rather obvious observation is that when you start blowing up the projective space and the toric strata, all the varieties that you see are toric. Okay, this observation is, seems rather obvious, but toric varieties are rational. So that will imply that if my pair is log rational, then all the strata of B must be rational, or at least in some resolution, because the argument that I was giving works in resolutions. Some resolution of the strata will be rational. So we have these 2 ways to test log rationality. At least this is, yeah, I mean, we have these 2 abstractions for the study of log rationality. And the conjecture is that these 2 abstractions are the only abstractions. So let me write the conjecture here. I was going to say theorem. I wish this was a theorem. So what we want to express with this conjecture is that checking rationality is not much harder than checking log rationality. It's just checking log rationality is the same as checking rationality of the strata, or some resolution of the strata, plus some combinatorial condition. So conjecture. So I have to mention that this was conjecture in dimension 3 by Tom Ducat, a former student of Miles Reed in 2023. And then we wrote with no more evidence, we wrote the conjecture in full generality. So let me write the full general conjecture is that let XB be a log Calabi-Yau pair. Assume that the dual complex is PL isomorphic to a sphere of dimension x minus 1, and now I will use some language that I haven't introduced, but it essentially means that the resolutions of the strata satisfies this condition. So every I don't want to get into these details right now. Every DLT strata of XB, including X, so when I think about the strata of this pair, I'm thinking about X as a strata, and this makes a lot of sense when you perform a junction, right? When you perform a junction to a component S, S becomes the ambient variety, so it's natural to think about it as strata. Is rational. So this, the DLT strata, for the experts, it just means the strata on a DLT modification. For the non-experts, you have to check this condition on a log resolution, okay? The rationality of the strata, right? Because it could happen that you have some singular point such that when you blow it up, you extract a divisor with coefficient 1 that is not rational, but is in X is getting hidden on a point. Right? This is very likely to happen, so we need to impose this condition on the DLT strata or some suitable log resolution of the pair. So what is the conjecture is that if you have these two conditions, then you're log rational. Then XB is log rational. So log rationality is nothing else than rationality plus combinatorics. But you know, this is just a conjecture. It's a very wishful conjecture. And it may be wrong, but it doesn't matter, because if it is wrong, I will add a new condition, right? I mean, this is a conjecture, but the important thing is that we're seeking how to understand log rationality, right? This is the main topic. If the conjecture is wrong, then we will have to find a way to fix it, if it is fixable, right? But we're trying to propose this new direction of log rationality that it has not been considered in algebraic geometry so far. So, are there any questions? Okay. So, in which cases do we know that the conjecture holds? So let me write some cases. In dimension 2, this conjecture is true. This conjecture holds due to work by Gross, Hacking, and Gross, Hacking, and Kiel in the 2000s. So actually, they were not trying to prove this conjecture, of course. They did this much before these notions. They were just studying mirror symmetry for local Labio surfaces, and they turned to do this observation that if the dual complex is a circle, and actually in dimension 2, the second condition is automatic. Because if the dual complex is a circle, you can prove that the variety is rational, and then the cycle must be a cycle of rational curves, so the second condition becomes vacuous. So they prove that if the dual complex is a circle, then they say that it has a toric model, meaning that you can do some blow-ups or blow-downs to get to a toric Labio pair. Okay, and then it was proved in dimension 3 in some very special case, and even this very special case is something pretty worth mentioning, and I was very impressed when I saw this. Dimension 3, proved by Ducat in 23 for pairs of the form P3, B. So actually, what was the first computation that we did in this talk, right? It was like the nodal cubic going to the conic plus the line going to the 3 lines. Essentially what he proves is that you can do the same thing in dimension 3, but in dimension 3 there are like 17 possible families, and the variable maps that you have to find between them are highly non-trivial. Some of them are explicit, some of them are just, kind of MMP constructions of blowing up something, running some MMP. Okay. So it's very beautiful work, and it allows you to understand a bit better what happens in the complement of these hypersurfaces, right? Because if you understand this map from P3 with the toric boundary to P3, V, then you may say a few things about the complement of B inside P3. So, okay, and I think this is it about the conjecture. We have some cases that have to do with some invariance called complexity. I think that Joshua Enright is proving this, that complexity 1 implies log rational. But okay, that's work in progress, I think. And okay, so this is it. So, oh well, there's one more case, but we did not. Okay, so let me mention a theorem that we prove with. This is not a very general case, though, and I will explain why. So we prove with Loginov, myself, and Vasilkov in 24. Actually, this paper was posted a few, maybe a month ago or something like that. So a general, a smooth, rational Fano threefold is log rational type. So of course this, and actually we can prove that all these words are necessary. There are some special elements that actually do not have nice elements in negative KX. There are some Gorenstein Fano threefolds that, although corregularity 0, they are not log rational type. And well, this one is pretty obvious. Okay, so we proved this, and why it's not a strong case for the conjecture is because for each x, we find a specific boundary that we can transform to P3, the toric boundary. It's not that we prove it for any possible boundary on any smooth Fano threefolds. And actually, this conjecture led to, this theorem led to some interesting questions about K3 surface that was not considered in the literature. Like if I think, okay, so this is, I think, is something that Loginov is doing currently, but this conjecture applied to the case of a smooth Fano threefolds implies some non-trivial statements about the generations of K3 surfaces that we don't know if this is true. We check with some experts, and it's very unclear. So let me, in the next 10 minutes, let me give you examples that this conjecture fails if you drop either of these two assumptions. Right? I mean, if we have the two assumptions, then it must fail. Of course, if you find an example that violates one or two, it's not log rational, but let me give you examples in which 2 is satisfied but 1 is not, and in which 1 is satisfied but 2 is not. Okay? Are there any questions? Okay, so the first example I actually mentioned yesterday. So there is a work by Kalogiros in which he takes birational superrigid threefolds and a boundary that has dual complex sphere. Yesterday I just say, sorry, yeah, actually yesterday. So remark, yesterday I just say corregularity 0, but actually the dual complex sphere. So there are examples by Kalogiros. There are examples by Kalogiros of X, a terminal Fano threefold, and terminal birational superrigid. This was the important part. Birational superrigid Fano threefolds and a V in negative KX with the dual complex of XB isomorphic to S2. So PL isomorphic to S2. So this condition holds, and of course this condition doesn't hold because we also ask X to be rational. And this is birational superrigid. And then the second example is quite beautiful. Is one, so far, one of my favorite examples in this theory is the following. Oh yeah, let me erase this. So example, so take P1 to the n power and take the toric boundary. I will just call it BT. The torus invariant boundary is just the pullback of 0, 1, 0, 0 and infinite for every possible projection, right? Well, you can take any 2 points. They are equal up to automorphisms. And then here you have an involution, right? In that sends P1 to the n to P1 to the n, and then it sends each pair xi yi into yi xi for each copy of P1, right? So there is an involution, and this involution clearly preserves BT. So what is the dual complex of this pair? What is the dual complex of P1 to the n BT? Well, this is just PL isomorphic. Well, actually, it's not PL isomorphic. It's equal to the boundary of an n-dimensional cube, right? This is how they intersect. And then you can observe that this involution preserves BT. So when you quotient by it, you get a Loeb-Calabi-Yau pair, XMBN. So this is the only boundary Vn such that the pullback of this with respect to the quotient is BT. So P1 to the n, comma BT, quotient by the involution, okay? So what is the dual complex of X and Bn? So you can actually check that this guy is still simple normal crossing. It has some singularities in the interior. You produce some singularities in the torus. Actually, the points 1, 1, yeah, all the points of the form 1, 1, 1, 1, 1, 1, negative 1, and so on. All these points are fixed by the involution, so you get a lot of singularities in the interior of the torus, in the image of the torus. But outside, you do not get singularities, the pair is simple normal crossing. So can some grad student tell me what is the dual complex? This is not a definition. What is the dual complex of this pair? Not you, maybe you. What is the dual complex? Oh, you cannot say it, you know it. What kind of projective space? Okay, there's someone complete your answer here. It's joint work, right? Pn minus 1r, right? Because essentially the involution is acting like the antipodal on the cube. So when you quotient, you get a real projective space. So now the hard question. So if a grad student answers this, I will get you a very nice bottle of wine. So question, why are the strata of Bn rational? Or why is Xn rational? So if you see this is inductive, this whole process is inductive. So if you argue to me that Xn is rational, then you know that all the strata are rational, and we will have an example in which this condition holds, but this condition does not hold, right? Hence, not log rational. Grad students, why is Xn rational? Nice bottle of wine or something else. Okay, no answers is Noether's problem, essentially, right? It's the rationality of ring of invariance of a function. So if you don't see it immediately, homework. Prove that P1 to the n quotient by the involution is a rational variety. It's a very, very, very beautiful example. Okay, good. So we have we have almost everything by now. I have 15 minutes. So okay, we're missing two things, right? So we were going down this diagram, and I have to tell you how to detect cluster type pairs and how to detect toric pairs. So sadly, for cluster type pairs, we have no clue. So this is the answer for now. So let me erase this conjecture. And this conjecture, I forgot to mention this, but we call this the log rationality conjecture. And you know, we have very little evidence, but the whole point of this log rationality conjecture is to, you know, try to at least motivate people to try to disprove it or prove it and try to understand what's really going on, how to detect log rationality. So then the next question is how to detect cluster type pairs. Cluster type. The answer here is who knows? So this this turned out to be extremely hard. So we have some very little data about this. Let me just mention some propositions. So in this paper with Enright and Figueroa, we proved that a cluster type surface only has A-type singularities. Okay, so essentially only toric surface singularities. This is what I mean with A-type. With the resolution is just a chain of rational curves. So we proved this, and there is a handful of papers that actually are not very geometric. They are mostly algebraic, in which people have been studying singularities of cluster algebra. So they take a spec of a cluster algebra, they try to look for the singular points. And the whole theory from the perspective of cluster algebras, that I have to repeat, we have some connections with cluster type Fanos, but it's not a very deep connection yet. So in their setting, they can actually give classifications of singularities depending on the dimension. They're pretty close to A-type singularity. But we don't know this. We suspect, let me write this as a remark, we suspect that cluster type Fanos, have singularities with a small fundamental group. This is my personal expectation. So A-type is just cyclic. So sorry, when I mean a small here, I mean a small rank. Small rank by one. Right, so you don't get Dn singularities that needs 2 generators, or you don't get E8 singularities that needs more generators. But this is just oh, wait. I should say, we expect that. And then something that is rather more annoying is that, well, this part I have to say that I haven't thought very deeply about this yet. But we, during the summer, discussing with Joshua, we found some examples of local surfaces that look something like this. So this was one local pair, the other local pair. So they have the same number of components. And then you look at the singularities inside, and then you have exactly the same singularities. They're not isomorphic, but you know the configuration of curves, some intersection numbers, they all look the same. They have the same singularities, and one was cluster type and the other was not. So this gave us the feeling that maybe there is no nice criteria for cluster typeness. You really need to do something quite different to detect this. Okay, so that's sad, but let's move on. But this is still a work in progress by Josh. So now let me get to the final part, which is detecting toricness. Right, so as we said before, you can, if you want to detect toricness, one quite great idea is to look at the automorphism of your variety. But sometimes that's not so easy, right? Because the way that I will compute the isomorphisms of a variety, if you don't tell me which variety it is, I have no clue. I will embed the variety in a projected space, cross my finger, and then first look for all the elements of PGLN that fixes the variety. Right, that's the first thing I will do. Right, but the point is that, as Daniela was explaining on Monday, I think this is not always the case that all the varieties come from PGLN. If it is toric, it should, so there is a better chance. But if I give you a toric variety with a very weird embedding, right? I take a binomial embedding of a toric variety, and then I do a nasty change of variable, and I tell you, tell me if this is toric or not. I promise you, super hard. I have tried some examples, and it's not very easy to see if a given variety is toric if you don't choose the appropriate coordinates. So let me tell you what we do from the perspective of the minimal model program. So there is the following theorem, or first let me write a definition. So definition, let X be a local Abel pair. Actually, for this definition, you don't need the pair to be local Abel, but this is the context, so let me stick to it. Let be a local Abel pair. The quotes complexity of XB is the following invariant, is the dimension of X plus the dimension of the Q class group, so you tensor the class group with Q, minus the absolute value of B. So what is the absolute value of B? Where the absolute value of B is the sum of the coefficients of B. So if we go back to the examples that we wrote at the beginning of this talk, we have this one. This one has complexity equal to 2. We have P2 and the conic and the line. This has complexity 1. And this one that has complexity 0. So don't mix it with complexity for torus actions. It's a different concept. Ha! There was an unexpected symmetry there. Okay, good. So, but I'm not claiming that V must be integral. It could be combinations. You can check that if you pick combinations of many lines in P2, then the complexity is still 0. So if you take a toric-Calabi-Yau pair, so in the toric-Calabi-Yau pair, you know that the dimension of the class group is precisely the number of rays of the fan minus the dimension of X. This happens in the toric case. So if you take a toric-Calabi-Yau pairs, this invariant is 0. And actually, this characterizes toric-Calabi-Yau pairs. So the theorem is due to Brown, McKernan, Sbaldi, and Young, and says the following. And then later on in 2022, with Roberto Sbaldi, we actually proved that there is a local analog for this criteria, and one can detect toric singularities by using a local version of this complexity. Essentially, you just change the class group of X with the class group of the localization, and then at a given point, and then you get an invariant that measures if your singularities are toric or not. But let me write the projective version. Brown is McKernan first, right? Sbaldi and Young in 2016, I think. Let X be a Calabi-Yau pair. Let X be a log Calabi-Yau pair. Then the complexity of XB is non-negative, and if the complexity is 0, then X, the round down of B is toric. So I'm not saying that the whole boundary is toric, but at least the ones that appears, X must be toric, and all the devices that appear with coefficient 1 must be toric, right? So what will be an example of this? You have 1, and when I say that it's toric, I mean for the same GM action, right? Because you fix the GM action here on X, and this one is torus invariant. So let me just say why I'm making that comment is because if you take this picture, right? If you take this picture with one line with coefficient 1 and a lot of lines with coefficient 1/2, well, you can always take 3 lines that are fixed for some torus action, right? But you cannot find a torus that makes all of them invariant for the same torus action. So this is why we can only round down in the statement. And actually, Joshua will explain a generalization, or not a generalization, but an improvement on this theorem on next week, in which he can write work with Fernando, in which they write an if and only if. They actually characterize pairs of complexity 0. So let's go back to. So I think I should start converging somewhere. I will just take 2 more minutes. So let's go back to this drawing that I did here with the classes of varieties. So and let me just complete what I started writing. So Fano varieties. Here we have rational Fanos. Here we have corregularity 0 Fanos that we explained that neither contains. And here I should say absolute. Then inside this you have log rational Fanos. cluster type, and toric. And let me tell you what is the detection principle for each class, right? Or the ones that we know at least. Here we say that we can use the anti-bicanonical test, which essentially is a fancy way to say, look at negative 2kx and negative kx. For log rational Fano varieties, we do not, but we at least have the log rationality conjecture, right? That says that log rationality should be the same as rationality of a strata, of DLT strata to be precise, but this is just a summary, plus a spherical dual complex. For cluster type, we still don't know. This is widely open, even for surfaces. For local Abiyao pairs of dimension 2, we don't know how to characterize cluster type-ness. For rationality, well, it will take at least 100 more years, I guess. And for toricness, we have complexity. Okay, so you can see that we have new classes of Fano varieties. We have, for some of them, we have good criteria how to detect if they are in the class or not, but there is still work to do, I think, especially here. And then let me just redraw the table that I drew the first day of a smooth Fano varieties. And I can tell you, I will just summarize what we know so far. So smooth Fanos. So we have the dimension, the number of families, and here I will write if they're rational, log rational, and with this I mean the general element, right? Because the special elements, I mean, in the families, all these conditions may vary. Actually, with Lina G, we're proving that these two conditions, being toric and being cluster type, is a locally closed condition on families of Fano varieties, but it's still work in progress. So toric. So what we know so far is the following. Well, in dimension 1, there is just P1. You go all the way down with ones. In dimension 2, there are 10 families. The general element of all of them are rational. The general element of all of them are log rational, hence and cluster type. And there are only 5 examples that are toric. Yes. In dimension 3, the number of families is 105. There is 88 that are rational. There is 88 that have log rational general point, right? This is what we prove by with Vasilkov and Loginov. So this is by Loginov, myself, and Vasilkov 24. Here, oh, I forgot the ones of corregularity 0. They should be somewhere. Yeah, sorry, let me add it here. Looks ugly now, but whatever. Corregularity 0. Here you have 1. Here you have 10. Cluster type, actually, we do not know yet this number. We're currently investigating which smooth Fano triples are cluster type. Toric, you have 16. And corregularity 0, you have at least 100. And this is by the work. This is by APL, Avilov, Priyakovsky, Loginov 23. And what about dimension 4? Well, dimension 4, we're exactly in the same place than before. We still don't understand. We're trying to clean the picture completely in dimension 3 before we start trying to do classification. I know. In dimension 4, so this is completely open. Well, I should write question mark here in all the in all of this, except here that there are 1 and 24. However, I think, or what we expect, is that this number is computable. That we have enough understanding of when a smooth Fano trifold is cluster type. This is work in progress, and the hope is that in the future we can classify a smooth Fano fourfold that are cluster type. And this is all I wanted to say.